Let's get into First Principles Daily, episode 35 for July 10th, 2026. Closing the week with one more look at where the next 10 times is hiding. Copper cables costing thousands per kilometer gave way to glass strands worth pennies once engineers treated data movement as a purity problem instead of a wiring problem. Copper wire once set the physical limit on how much information could move between cities. Electrical resistance and the skin effect forced engineers to add repeaters every few kilometers and accept data rates that topped out in the low megabits. A different approach asked what would happen if the carrier were light traveling through glass instead of electrons traveling through metal. The answer required glass so free of impurities that a pulse could cross tens of kilometers before fading below detection. For most of the 20th century, long-distance communication relied on copper pairs or coaxial cable. Designers improved performance by increasing conductor diameter, adding loading coils, or installing more frequent amplifiers, yet each step remained inside the same electrical framework. The finished cost of a copper trunk line therefore reflected the price of refined metal, insulation, and the labor of splicing heavy reels every few hundred meters. Because the physics of electron flow in metal was treated as fixed, incremental gains in bandwidth came at steadily rising expense. Telephone companies and equipment suppliers accepted these costs as the natural price of moving voice or early data traffic. When demand for video or internet traffic appeared, the same copper plants simply could not scale without prohibitive numbers of new cables and repeaters. The convention persisted because every prior network had been built the same way and because the capital already sunk in copper infrastructure made alternatives appear risky. Under that approach, the cost per bit stayed high enough that widespread consumer video or cloud-scale computing remained economically out of reach. The skin effect concentrated current near the conductor surface at higher frequencies, so simply raising voltage or frequency produced rapidly growing losses rather than usable capacity gains. Coaxial designs tried to mitigate this by surrounding the center conductor with a shield and dielectric, but the shield itself added weight, cost, and another set of failure modes at every splice. Loading coils reduced distortion on voice circuits, yet introduced their own inductive limits once data rates climbed above a few kilobits per second. Each of these refinements treated the metal path as immutable and therefore concentrated effort on compensating for its shortcomings. The resulting systems required continuous power feed to line amplifiers, frequent maintenance access, and heavy mechanical support structures, all of which compounded the installed cost. Because every incremental improvement still operated inside the same carrier physics, the industry came to view rising expense per added bit as an unavoidable feature of progress rather than a signal that the carrier itself needed re-examination. The decisive shift began by discarding the assumption that the carrier had to be electrons in metal. Light and glass offered far higher frequency and therefore far higher theoretical bandwidth, but only if the glass itself did not absorb or scatter the photons. A rough magic wand estimate starts with the raw material. High-purity silica is refined from ordinary sand whose commodity value sits on the order of a few cents per kilogram. Even after accounting for the small mass inside a kilometer of fiber, the material floor lies well below $1 per kilometer. Early copper cables, by contrast, carried finished prices measured in thousands of dollars per kilometer once drawing, insulation, and installation were included. That gap produced an idiot index in the high hundreds or low thousands. The index is calculated by dividing the finished part price by the raw material cost inside it. When the finished cable reached thousands of dollars while the metal itself sat at a small fraction of that amount, the ratio climbed into the hundreds or low thousands. The gap lived almost entirely in the manufacturing steps required to reach the necessary transparency. The first concrete move was the development of vapor phase deposition processes that could reduce transition metal impurities to parts per billion. Instead of melting and drawing ordinary glass, engineers created a preform by reacting silicon tetrachloride and oxygen inside a rotating tube, depositing layer after layer of ultra-pure silica. Each added layer removed another source of absorption, driving attenuation from hundreds of decibels per kilometer down to fractions of a decibel. That single process change eliminated the need for repeaters every few kilometers and thereby removed the dominant operating cost of the copper system. Objections that such purity could never be maintained at scale were met by continuous flow reactors that grew preforms large enough for hundreds of kilometers of fiber from a single run, keeping impurity levels consistent across the entire length. A second move addressed the light source itself. Early optical links still used bulky gas lasers or LEDs whose cost and lifetime kept the overall system expensive. Semiconductor diode lasers, once they reached sufficient reliability and spectral purity, replaced those sources. Because the lasers could be fabricated on wafers and packaged in volume, their unit cost fell by orders of magnitude while their electrical to optical efficiency rose. The lower drive power and smaller size also reduced the power and cooling infrastructure around each terminal. Trade-offs such as wavelength drift with temperature were managed by adding simple thermoelectric stabilizers, whose added cost was far smaller than the savings from eliminating gas laser maintenance. A third move refined the fiber drawing step. Preforms that had been painstakingly built by hand were replaced by larger, more uniform preforms produced in continuous chemical reactors. The drawing tower itself was instrumented so that diameter variations stayed inside a few micrometers, preserving the waveguide properties without post-processing. Each of these changes attacked a different term in the cost stack. The preform purity step attacked attenuation. The laser step attacked terminal equipment cost. The drawing step attacked labor and yield loss. Together, they moved the finished cost of the transmission medium toward the raw material floor, while the remaining system costs shifted to amplifiers and trenching. The cumulative effect was a sustained decline in cost per bit of roughly 2 orders of magnitude per decade for several decades after the first low-loss fibers appeared. Long-haul routes that once required heavy copper or microwave towers could now be served by hair-thin strands whose material content was measured in grams. The idiot index of the fiber itself fell dramatically once the deposition and drawing processes matured. The index for the complete installed link remains higher because of permitting, trenching, and the optical amplifiers still required every 80 to 100 kilometers. Those amplifiers, splicing crews, and rights-of-way constitute the stubborn remainder that has not yet reached the physical floor. Exact current figures vary by route and operator, yet the order of magnitude improvement in delivered bandwidth per dollar is well documented in public telecommunications records. Dispersion and nonlinear effects still impose practical limits on how far a single wavelength can travel before regeneration or compensation is needed. The physical act of burying or suspending cable continues to dominate project budgets in new corridors. Yet the core transmission medium now operates close enough to its material floor that further gains come mainly from wavelength multiplexing and improved amplifier spacing rather than from redesigning the glass itself. Redefining the carrier from electrons in metal to photons in glass compels every downstream cost to be re-examined against the new constraint of photon loss rather than resistive heating. The same re-examination appears whenever an entrenched infrastructure continues to add compensation layers, because earlier capital commitments made the original physical path appear permanent. Tomorrow, the show returns with another concrete case or another domain whose raw material floor sits far below its present price. Which everyday object still carries an idiot index measured in the hundreds because its designers have not yet asked what the atoms alone would cost? That's a wrap on today's first principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. And before you go, this show is part of the Nerra Network, a family of daily podcasts on tech, science, and markets, each one a short, sharp briefing you can finish on the commute. If today earned its place in your feed, here's your next listen. OmniView, a balanced daily world news briefing that takes every side seriously. Find every show free at nerranetwork.com. New to the network? nerranetwork.com/start-here picks the right daily briefing for you in about 2 minutes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.
I'm about to prove